Hello, today we have our third video in our acid-base unit, and this one will talk about pH, how to calculate pH, how to calculate the pOH, the hydrogen concentration of a solution, and the hydroxide ion concentration of a solution. Hopefully you might remember some of this from Regents Chem, and if you don't, we're going to go through it all anyway, so that's okay. All right, first off, we have the ionization of water. So all of our acids and bases are in aqueous solutions, so therefore we would have water present. And water is going to ionize on its own to an incredibly small amount. So if we take water and show its ionization by this equation here, this would be our K expression because we would leave the H2O out because it's a pure liquid. That K we call Kw for ionization constant of water, and it has a value of 1 times 10 to the negative 14th. So this is why the pH scale is based upon 14 because of this value here. So if we have pure distilled water at 25 degrees Celsius, there would be an equal concentration of hydronium and hydroxide ions, and they both would have a value of 1 times 10 to the negative 7th, and it would be a neutral solution because we'd have an equal amount of hydronium, an equal amount of hydroxide. Since our K value is going to be constant, we can calculate either the hydrogen ion in solution or the hydroxide ion in solution if we know one of them. So that's what we're going to be working on next. All right, so if we have our hydrogen concentration, then we can do the hydrogen times the hydroxide equals 1 times 10 to the negative 14th. So let's say the hydrogen concentration was 1 times 10 to the negative 8th, then the hydroxide would have to be 1 times 10 to the negative 6th in order to equal our constant value. What we often talk about, though, is pH or pOH. So our pH is the negative log of the hydrogen concentration. This formula is on your reference table along with all of these formulas on this slide. So if we have the hydroxide concentration, we can calculate what's called the pOH. And since everything is based upon 14, since our ionization constant for water is 1 times 10 to the negative 14th, pH plus pOH equals 14. And if you know the hydrogen concentration, if you know the pH, you can find the hydrogen ion concentration, and if you have the pOH, you can find the hydroxide. So basically, if you know one thing, you can figure out everything else. All of these formulas are on your reference table, and we're going to become very good at this throughout this unit. So this here is just showing, if you have one, you can figure out the other, and we'll be working through a couple of examples to work on these skills. This slide here just gives you a frame of reference on some things that are, that we might encounter in everyday life. Like we know that lemon juice is pretty acidic. So its hydrogen concentration would be 1 times 10 to the negative 2nd. So then the hydroxide would be 1 times 10 to the negative 12th. The pH would be 2 and the pOH would be 12. If we took a look at bleach is going to be basic. So it's going to be right here in between these ranges. Before we get to our examples, I just have to go through a real quick note on pH and significant figures. So in pH, only the digits after the decimal are significant. And that's because it's a log function. So therefore, if our pH is 2.79, we only have 2 significant figures. 11.65, we would have 2 significant figures. 13.1, we would just have 1 significant figure. So just count your decimal places for the significant figures. Okay, so now we're going to take a look at our first example. Our pH is 2.79, and we are looking for the hydrogen concentration. Now, obviously, with a pH of 2.79, we have an acidic solution. And if I look at my reference table, the hydrogen concentration is equal to 10 to the negative pH. So all we do is 10 to the negative 2.79. We plug that into our calculator and get our answer. And that would give us 0.0016. This has two significant figures, so we would want our concentration to have two significant figures. Of course, we could express this in scientific notation also. Additionally, we could have found the pOH and the hydroxide concentration had they asked us to do those things. All right, so in this example, we are finding all of our different things. And we could really honestly go in any order, it doesn't matter. So we're given the hydrogen ion concentration and asked to find everything else. So if we just want to go in order, we can use Kw is equal to H plus times OH minus. All right, and that has a value of 1 times 10 to the negative 14th. So if my H plus is 2 times 10 to the negative 6, then I can just divide those in order to find my OH minus concentration. All right, once I plug that all into my calculator, I get the hydroxide ion concentration to be 5 times 10 to the negative 9th. All right, next up, if I want to find pH, I use the formula in the back of my reference table that pH is equal to the negative log of the hydrogen concentration. So I will do negative log of 2 times 10 to the negative 6. So I will just put that into my calculator, and that will give me the pH. And I get 5.698. I only want two significant figures, so that's going to be 5.70 for my pH. Next, I have the pOH. So for the pOH, I can use the formula of pH plus pOH equals 14. So if my pH is 5.7, and I'm looking for the pOH, I am just going to do 14 minus 5.7, and that would give me the pOH, which is equal to 8.30. And lastly, is this solution acidic, basic, or neutral? Easiest way to do that is to look at the pH. Since the pH is 5.7, then we know that we are acidic because it's less than 7. Now, again, you could have gone in a different order. From the H plus, you could have found the pH first and then used the pH to find the pOH and then the hydroxide concentration. So as long as you can get all the different values, you are great. All right, in our next example, we are looking for the pH of a 0.011 molar solution of HBr. So first thing we have to recognize is that HBr is a strong acid. Therefore, it will 100% ionize in solution. So if I have this concentration of my acid, I also would have that concentration of the hydrogen ion because that will ionize 100% in solution. This will not be our case with our weak acids. We'll have to do a K calculation, but we'll get to that later. So if I have my hydrogen concentration, then I can easily find my pH, negative log of the hydrogen concentration. So this would just be negative log of 0.0011. I plug that into my calculator. And when I put that into my calculator, I get 2.95. And, 2.96 actually, once I get that rounded properly. And this had two significant figures, so therefore with pH, we have 2 digits after the decimal. All right, last problem. Here we have the pH of a 0.0011 molar solution of calcium hydroxide. All right, so we have to recognize that that is one of my 8 strong bases. Now, when calcium hydroxide ionizes in solution, we are going to get the calcium ion, which is in no way going to affect the pH, but we are going to get 2 hydroxide ions. Therefore, the hydroxide ion concentration is going to be equal to 0.0022 molar. So then what I would do is I would find the pOH. So that's going to be the negative log of the hydroxide concentration. So negative log of 0.0022. So we'll plug that into our calculator. And that gives us 2.66. From there, then I can find the pH. So then in order to find the pH, it would be 14 minus the pOH, since I add up to 14. So it would be 14 minus 2.66. So the pH would be equal to 11.34, which makes sense since we are dealing with a base. Now, additionally, from the hydroxide ion concentration, we could have figured out the hydrogen ion concentration and then found the pH. So there are going to be different ways to attack these problems.